Newton's second law is going to be building off of Newton's first law, where Newton's first law said if the net force is zero, the acceleration is zero. So what Newton's second law tells us is that if there is a net force, if there is an unbalanced force, then acceleration. That means an object can be doing one of three things: speeding up, slowing down, or changing directions. And we're going to mathematically determine this by the relationship between acceleration, force, and mass. So acceleration is the ratio of the force applied divided, or more commonly, you'll see it written as the net force equals mass times acceleration. So what we're going to look at is just some different scenarios where things would be accelerating and understanding how we would set the force diagram. The first scenario would be projectile motion. So we just got through that unit. So projectile is anything that's traveling through the air with the only force acting on it being that of gravity. So have the force of gravity always pointing straight down. Doesn't matter where it is, the force of gravity is going to be pointing straight down towards the surface of the earth, right? The net force then could be calculated as just the force of gravity, and that's going to equal mass times acceleration. This actually then can get us the understanding that, well, what is the acceleration that a projectile is going to experience? The only acceleration it's going to have is that of gravity. And so what we see is then that the force of gravity can be calculated by taking the mass of the object, this is in kilograms, and multiply it by little g. We can simplify it by just using 10 or 9.8 if we want to do in a lab scenario. But this solves for our actual value of finding the force of gravity using Newton's second law. Whatever the mass is times little g is going to give me my force of gravity. And we're going to use that often and a lot. We're going to use that often throughout the rest of the year, and especially in this unit. Another scenario is an elevator, where an elevator usually you're going to be moving at a constant velocity, but for you to start moving, you have to accelerate. So if you're moving upwards, you have a moment where you're going to be accelerating upwards. If that's true, then the net force must also be upwards. So what are the forces acting? Now I have this, and you'll really see scenarios where people are standing on a scale, right? And what's true is this person has two forces acting on them. One is the force of gravity, acting straight down. The other one is the normal force of the scale pushing up. Now, if it is accelerating upwards, the net force must be upwards. That means that this scale must have a bigger force than the gravitational force. So if we were to find the net force, the net force would look as the net force in the y direction is the normal force minus the force of gravity. So is that the force of gravity is mass times little g. So I'm going to rewrite this as we could then, okay? And you have to pay attention in terms of what the direction of my acceleration. And this would be a positive acceleration, right? Which would actually give me a bigger normal force. So I have a sense of being heavier as the object is being accelerated upwards, right? If the car was, or if the elevator was accelerating downwards, that would be a negative acceleration. And that would actually make the normal force smaller than gravitational force, because for me to have a net force downwards, gravity would have to be bigger than my normal force. And so that, based on your net force, you have that acceleration downwards. Another scenario then, or some incline. So we have some incline that is some angle theta up. Here are the forces. Now what we're going to do is, because objects typically wouldn't move like this, they are typically going to move in this direction, is we're going to tilt our x and y axis. So now we're going to say our x-axis, our positive x-axis is down the ramp, where our positive y-axis is up perpendicular, going straight down. So we draw it straight down, not perpendicular to my surface. The normal force, if you remember, is always perpendicular to my surface. So I draw that in the positive. Now what we see is we see a of theta, because that is my adjacent side. Okay? Now in this case, we can look at what are the net force equations. Also circumstances, sometimes you might frictional force. Right? If something is sliding down the ramp, the frictional force would point up the ramp. If something was sliding up the ramp, the frictional force would point down. It all depends on the direction of the motion. And we'll talk about friction more specifically in another video. But let's do the net forces if we do have friction here. What I'm going to do first is the net force in the x direction. What I see is the parallel component pointing up. So that gives me my parallel force minus my frictional force equals mass times acceleration in the x direction. If I wanted to write that out a little bit more, that would be my parallel force. If I wanted to write that out a little bit more, I could plug in this for my parallel force, which is force of gravity times the sine of theta minus my frictional force equals mass times acceleration in the x direction. And I can now plug in mg, because force of gravity is mg. My parallel force minus my frictional force equals my mass times my acceleration in the x direction. And that's typically the direction that we're going to be accelerating in, either up or down the ramp. If it's moving up the ramp, usually it's slowing down. If it's moving down the ramp, usually it's speeding up. Okay? Looking at then for my y direction, I see two forces. I have my normal force and I have my perpendicular force here of gravity. So that equation is going to look as the normal force minus my perpendicular force equals my mass times my acceleration in the y. Now, just like an object sitting at rest on a table, we're not really accelerating in this direction or this direction at all. We're accelerating parallel to the ramp, but not the entire side of my equation is 0. That can then say that my normal force is going to equal my perpendicular force, which if I plugged in what perpendicular force is, it's the force of gravity times the cosine of theta. Force of gravity is mass times gravity, so I can have my normal force as mass times gravity times the cosine of theta. And that's typically how we're going to set up problems that look like this with forces on a ramp. Again, things that could change is if my frictional force is the other way, right? This is something that maybe is moving down the ramp. If the object is moving up the ramp and there's friction, the last scenarios are ones that are considered Atwood machines. And these are pretty common setups that you'll see where you have some pulley with two different masses on either side. Typically they're differing of masses. And you're gonna look at how those forces are acting on the system. So to do that, let's look at this scenario first. What we have on each force is we have a force of gravity